Hello, in this video I will be discussing rotation, and more specifically I'll be looking in depth at rotational kinematics. One sec. Okay, so starting off with what angular displacement is. Essentially, angular displacement is represented by this sign, and it just represents the change in position and the distance traveled in terms of change in s. So a common formula used when referring to angular displacement is s is equal to r, which is radius or distance times angular displacement. So next I'm going to talk about angular velocity. So angular velocity is used when exploring rotational motion, and it's the same thing as velocity, but it factors in rotation. So angular velocity can be defined by the following formula. Angular velocity is equal to the derivative of the displacement. Next, I'm going to talk about angular acceleration. So angular acceleration, again, like acceleration, however, it takes into account the factor of rotation. So angular acceleration is modeled by the following symbol, something like that. And a common formula for angular acceleration is the derivative of the angular velocity. So this might seem familiar because it's very similar to translational kinematics. So now that we've got that down, I'm going to go ahead and read the statement for a practice exam problem. So a particle of mass m moves counterclockwise around a horizontal circle of radius r as shown above. The angular speed of the particle is given as a function of time t by angular speed of t is equal to bt, where b is a positive constant and t is greater than 0. So I'm going to go ahead and model this figure. So we've got our particle right here. We go ahead and label that particle, and we know that it is moving in this direction. And then we've got the center and the radius of this circle. So problem number, and we are given that W of t is equal to bt. So problem number 31 specifically asks, which of the following best describes the acceleration vector for the particle at the moment shown in the diagram? So the first thing I would do when looking at this is to note that angular acceleration, if we know angular velocity, we can find angular acceleration by finding the derivative of the angular velocity. So essentially we just take the derivative of bt dt, which simplifies out to is equal to b. Since we know that the derivative of t over the derivative of t is just going to be 1, and b is a constant from the problem. So next we're going to look at the acceleration that is tangential to the particle. So this is going to be acceleration t, and this is going to be the acceleration, the radial acceleration. And we want to find the net acceleration. So we know that the acceleration, the tangential acceleration is going to be equal to r times the angular the radius times the angular acceleration, which is equal to r times the constant b, which we solved right here, r times b. And then we go ahead and we do that for the radial acceleration as well. So a radial is going to be equal to b times the, it's going to be equal to the angular velocity squared times the radius. So we know that the net acceleration, therefore, is going to take into account both the tangential and the radial acceleration, and thus, and since we got positive values here, we know that the positive direction is this way for the acceleration tangential and this way for the acceleration radial. So thus we can conclude that the net accelerations is going, both components of the acceleration will point, one of them will point to the left as shown here, and one of them will point to the bottom of the page. So we go ahead and we reference that with the options, and options E reads, it has components directed toward the left and toward the bottom of the page. And thus we can conclude that option E will be the correct answer for this problem. Okay, thank you.